in the last lecture we talked about the density matrix. So density matrix, the element element nm was 1 over n is equal to 1 to n or n k function of the time. So first is the complex quantity. So we talk about this matrix, and we say that if you want to find the average of any a statistical quantity, so this will be, the average will be sigma n, sigma k 1 to n. We needed to write the average of this operator and each element of the ensemble. Like that. This is a normal averaging. So this is the arithmetic averaging. So it's just normal averaging. The difference is that the average in each ensemble should be calculated from the density matrix. So this becomes like n or n k star g and m or m k. Where g and m was defined by the phi and star, this g phi and d tau, or n g m is another representation of that. So, and by replacing this and just by changing the sigma, we show that it will be reduced to the trace key row over trace row, because sometimes the trace row is not 1. I mean the trace row is, what is the trace row? Sigma n, diagonal element of this row and n. Sigma n, what is the row and n?
1 over
This is an m, so 1 over n, sigma k 1 to n, r n k star r n k. 1 over n, sigma n, sigma k, r n k t square. And this sigma we can write like by interchanging the order of the summation. We write like that. And you remember the INK was the probability of the, this is the probability for finding ensemble labeled by k in state phi n, so with energy n. And this probability, the sigma, if the wave function be normalized, only that, I mean inside the bracket, if phi n star, phi n d tau be 1, then only with this condition you can put the sigma n1. Or if the psi k star psi k d tau be 1, only that. But not always. So you can have the wave function for the element k, but the wave function unnormalized. This is the normalization. So if you have the normalization, you can take this one, and by these conditions, it will be sigma n k 1 to n 1. So it will be 1 over n, it will be 1. Only that. But in general, as I told you, you can have the unnormalized, you can have unnormalized wave functions, cycle. I mean, you can have a cycle square eta not 1, not equal to 1. In this case, you needed to keep the tracer rule. So we keep tracer rule in the case for the security. So we keep a tracer rule, so that's more safe. The second proof was that I was trying to prove a theorem for the rule. So the theorem for the rule was that rho square should be rho. Yes.
There in the expectation value of G and M. Can we write by alpha n alpha or n G m? We can write it also by alpha n G alpha n.
What is the alpha?
The expectation value.
What is the alpha?
Which is the one with the basis.
Phi. Phi, yes. You can write it this. This is a yes. Phi n G phi m. Yes. Another. Yes, you can write it like that. All the same. So the next things which I tried to prove was that the rho square matrix is just rho. So let me to back again to this proof. And for general, you know, for the case when you have a micro-canonical ensemble, I will write now, a few minutes later. So the proof is very easy for that. I want to write in general to see that what happened again, because last time so I want to write the element of n, m of this matrix. So will be rho, n, m. So according to the matrix product, you know that again I write A, B, and M is sigma L, O, and L, B, and M. When you two matrix, you read it before several places. So we write that like a rho n L, rho L, M. So let me to replace that each component here 1 over n sigma chi 1 to n a n chi star a l k. And what about that 1 over n sigma k prime, another index a l k prime a m k prime. We have a one. These two indexes are referred to the summation over the ensemble. They are very completely different, and these indexes running from the over the n or over the l. So this is from the quantum indexes, actually, if you can call it that. I don't know indices. So first, I wanted to keep it all of this outside, and the ensemble index is very risky to work with that. We have the index L, so I want to just first concentrate on the terms which we have a L. Okay, and that's if you can make it more simplified, we have to see that what happened for that, if we can make it this simplified, more simplified of that. What is this? Roye to see that how we can make it more simplified this expression. We have a, because the proof which is given in the book is just for microcanonical, so for microcanonical it's very trivial to prove that. I wanted to prove generally, so this is a challenge, so I don't know that we can do that now or no. Okay, let's try this. So what we know is that, as I told you before, we know that Rn k t squared and x over the k or the n is 1, as I explained that before, was if the wave function are normal. What is the An k? An k was the, you remember how was the definition of that? We need to write, you know, psi kt was sigma An k t phi n, huh? These were the coefficient for the wave function for the element k, and phi n was the stationary or independent wave function. Okay, what was the An k? An k was integral of phi n star psi k d volume. Tau was the volume. But let's me to try to calculate the things which we have here. RL k prime star RL k. What is that? I know it will be the delta chronica, but I want to show that actually. I want to say that this existed and is non-zero only when k is equal to k prime. And if k is not equal to k prime, it will be zero. But why? I want to prove that. Sigma L, so I want to replace Al k prime from here. So remember that will be phi L star psi k prime d tau, but whole should be a star. Al k from here, phi L star psi k d tau. Okay, let me do little bit more simplify that. Sigma L integral phi L psi k star d tau prime integral phi L star psi k d tau. And the volume are different also. Yes, this is for one volume. I mean, you have, for example, x here, and this is a tau x. But here you have another thing, x prime. So you have to be very careful when you want to repeat one integral two times. This is a one integral I know. I want to repeat that two times, one time with the star and one time without this. But they are different things actually. They are like a sigma. They are like two sigma and you want to multiply to that, of course it should not be like A n by n. Because it will be some other terms. It's not like A1, B1, A2, A2, B2, A3, B3. It has A1, B2, A1, B3, A2, B3. So how I can include all? Just you double sigma make everything clear. Like here, each term should have different index. So this is like index for me, this integration. So one time it appears with x, one time it appears with x prime. So let me to see that what will be the result. I wanted to write the integral and let me to see that it's very interesting calculation actually. Psi k prime x prime star psi chi x, and here you have a 1 sigma again. Phi Lx prime. You don't know that, but by doing this calculation, now you are doing representation theory. This is the modern mathematical physics tools for quantum field theory. I just replace it. You don't need to know the name. If I can tell you that what is that, so everything will be solved, What is this? How I can write sigma LFE, L star x prime? I needed to. We have a function. Any functions, some things you need to know that. I write here in the brackets. This phi Lx, which L can start from any, it depends to the level of energy, Energy level maybe start from 0, like harmonic oscillator, maybe start from 1, like hydrogen atom, like particle in the box, and is from the 1 to. So L starts from something and runs to the infinity. Energy levels can be empty. Look at that. They are a complete set of functions. That was the thing which I asked you. Remember 2 lectures before I asked you to read the chapter 5 of the Greiner because of this only. One reason was that. Okay, I don't know that you'll find time to read it. That I want to just very quickly review, but it's not enough actually. Complete set of the function means that any functions can be expanded in terms of this function. Any functions, like fx. And what is the AL? AL is integral phi L star x fx d tau x, the volume. Completeness. Any function means any function. So a special function, they call it delta Dirac. If you find AL is very interesting for delta Dirac. Will be delta Dirac x minus x prime phi Lx dx. According to the property, delta function multiply to any function and take the integral. It gives you just the value of the function, and you have to see that in the electrodynamics somewhere there, or the delta Dirac. If you never read that before in mathematical physics. And look at that, what happened. So delta Dirac is sigma phi L, of course, a star, because coefficient should comes by a star. Yes? Oh, this is very important, this, and that will be a key to solve this problem. So I can now replace the delta Dirac here. Can I continue that here because I needed this So I will be d tau x prime psi prime x prime psi chi x delta x minus x prime, yes? Delta multiplied to any function gives you the value of the function at the point. So delta y multiplied to that, for example, by the integral of the x altogether gives you psi chi x prime. So will be d tau x prime. They are not, okay, let me to finish that. After that I want to tell you something. And this is, what is that? Integral psi chi x prime square d tau x prime. And we're talking about the normalized functions.